before. So I think at least now you can see the screen.
Sure. Okay, so hello everyone. Welcome to the third day of the bootcamp. Today will be okay. So today we have a day about optimal transport, and Mikaela Iacobelli accepted very nicely to give us a talk on a crash course on optimal transport. So thank you, Mikaela.
So thank you very much for the invitation to this very nice program. I'm honored to give this short lecture on optimal transport. So it's a crash course, so I will cover quite a lot of basic material, but without entering too much into details and proofs. I will write on the iPad as I were in, let's say, as with a whiteboard. I hope you will see it. Please, if you don't see something, tell me to Zoom, I will do it. So, the outline of this presentation is the following. I will first start with a brief introduction to the problem of optimal transport. Then I will introduce the Kantorovich duality, that is a very important tool in optimization also. And then I will arrive to the core of the optimal transport theory, that is Brenier's theorem, is one of the fundamental theorems in the theory. Then I will pass to the definition of Wasserstein distances, Wasserstein space, and the goal is to give an informal introduction to gradient flows in Hilbert spaces, the Benamou-Brenier formula, to finally arrive to a formal introduction of Otto's calculus to show that the heat equation is the gradient flow in Wasserstein on the end of the entropy. Can you hear me well?
Yes.
Okay, perfect. So let me just give you some references. Some are quite classical. There are two books by Cédric Villani. One is Topics in Optimal Transportation, is the first one he wrote in 2003. Then I read some parts of these books by Ambrogio Gigli e Savary, that is about gradient flows, in particular gradient flows in metric spaces and in the space of probability measures. So it's a very, very complete let's say, reference on gradient flows, much more than what I would say today. Then more recently, there have been this contribution by Filippo Sant'Ambrogio that is called Optimal Transport for Applied Mathematicians, so very centered in the topic. And then Couturi-Perret wrote in 2018 a book on computational optimal transport. And finally, Figalli-Glaudo wrote a book that is called An Invitation to Optimal Transport, Wasserstein Distances and Gradient Flows in 2021. And this is, let's say, a very introductory book to the topic. So if you then will need more precise references, just let me know and I can provide some more detailed references. But in all these, essentially in all these books, you will find what I will talk about today in a way or another. So I'm trying to move, okay. So let me start with a very brief overview. Okay, can you see well?
Yes.
So the problem of optimal transportation has been first introduced by Gaspard Monge, a French mathematician, actually a French engineer in 1781. In a way, just to answer to a very practical question. The question is, assume one extracts soil from the ground to build fortification. What is the cheapest possible way to transport the soil? So imagine that, like here, we have this amount of soil that we want to extract, and we want to bring it to build a fortification. So we want to transport, in a sense. Here we don't have probability measure, we don't see probability measures, but we can think that this distribution of soil is distributed like a probability measure mu, and this construction, this building, is a probability density nu. And we want to find the cheapest possible way to bring this mass from one place to the other, and cheapest in which sense. So to formulate this question rigorously, one needs to specify how much one pays to move a unit of mass from the point X that I pictured here to the point Y. And in Monge's case, the ambient space was R3, and the cost was simply the Euclidean distance, so the travel distance. Now, this was the most classical formulation of optimal transport. Then many years passed by until Leonid Kantorovich in the 40s, essentially in the 40s of last century, proposed a new, let's say, more modern version of the optimal transport problem. Let me remark that in Monge formulation, the optimal transport problem is deterministic. So I'm saying that there is just one point where the mass that is in X can only go in a point that is Y equal T of X. Okay. In 1940s, Kantorovich instead proposed a different notion of optimal transport that could take into account some non-deterministic situations that are very common in real life. Let me present it with an example. So suppose that we have several bakeries, B1, Bn. Here I pictured 3 bakeries because B1, B2, and B3 are the bakeries, and several coffee shops, C1, C2, C3, and C4. So let's say Cj, J goes from 1 to M. These bakeries are located at points xi, and they sell a quantity of bread that is alpha I. Let me write it. So this is bread produced by B1. And this is the position. I mean, the label that I do to this bakery. Let's say label. So these coffee shops instead are in positions YI, and they buy a quantity of bread that is by beta J. So let me now change. So I hope you can still see well. So okay, alpha I larger than 0 is the amount of bread produced by the bakery Bi. Beta J larger than 0 is the amount of bread that is bought, needed by the coffee shop Cj. So we assume, the first assumption is that the offer is equal to the demand. So the demand is sum from J that is equal from 1 to M of beta J, and the offer is sum from I that goes from 1 to N of alpha I. And we normalize everything to 1 because we want to deal with probability measure in the end. So now this problem is incompatible with Monge formulation because each bakery may supply bread to multiple coffee shops, and one coffee shop may buy bread from multiple bakeries. So for this reason, Kantorovich introduced a new cost formulation. So given C of xi yj, this is the cost to move 1 unit of mass from xi to yj. It looks for matrices gamma ij, I that goes from 1 to n, and j that goes from 1 to m, such that we ask for the following assumption. A, gamma ij, is it large enough how I'm writing?
Yes. Yes.
Okay. Gamma ij is larger than 0. That means that the amount of bread going from xi to yj is non-negative. B, for every I, sum over j that goes from 1 to m of gamma ij is equal to alpha I. That means that the total amount of bread sent to the different coffee shop is equal to the production. C, for all j, we have that sum from I that goes from 1 to n, gamma ij is equal to beta j. So the total amount of bread bought from the different bakeries is equal to the demand. And finally, D, that gamma ij minimizes the total cost, that is sum over ij from 1 to n and m, gamma ij c of xi yj. So, okay, so the total transport cost is minimized. So it's interesting to observe that the constraint A is a convex constraint, while B, C, and D are linear with respect to gamma ij, so linear. So in a sense, we are just trying to minimize a linear problem with convex or linear constraint. So this already shows a bit why this formulation can be very handy. Let me just come back 1 second to the picture just to show. Here I pictured a quick example, and I show you how to compute the gamma ij. So for example, gamma 33 is alpha 3 because the bakery B3 only sells bread to C3. And gamma 23 is beta 3 minus alpha 3 because it has to compensate the fact that the coffee shop number 3 receives bread also from the bakery B3. Is it clear, this simple example? Can I go on? So I assume yes. So if there are no questions, I go on. So optimal transport has attracted a lot of interest over the years in application due to its connection to several areas of mathematics. And in particular, all the applications are heavily linked to the geometry and also to the choice of the cost function C of x and y. So for example, let me just mention few applications. So there have been applications to the study of the Euler equation, isoperimetric inequality, Sobolev inequality, etc. But also in the study of evolution PDEs, like porous medium equations or dt of u. This is a bullet equal to lambda of u to the m, or dt u equal divergence of grad w convolution uu, and so on. And for example, in these situations, the most commonly used cost is the quadratic cost. So C of x, y equal to x minus y square, or for example, so in RD, this in RD, or also C of xy equal x minus y to the p, with p strictly larger than 1. But also there have been several applications to probability and to kinetic theory. So kinetic theory is my main, let's say, area of research. And so, for example, the optimal transport, in particular with the cost either C of xy equal x minus y, or with the quadratic cost x minus y square, have been used a lot for the study of transfer equilibrium for kinetic equations, or for stability, for example, for the Vlasov-Poisson equation, and to study the derivation of these equations of plasma physics from the N particle models. So it's a very useful tool. And also for the study of Ricci curvature on Riemannian manifolds. And here the cost is still quadratic, but is in most cases the Riemannian distance d of xy square. Okay, so of course there are much more applications, but I'm sure you will see plenty of application in the next lectures. Let me now go on with the notation. So the notation I'm using is really classical. You have already seen it in previous lectures, but just for simplicity, I will focus on the case of the Euclidean quadratic cost for most of the time. So cost equal x minus y square on Rd. So this will be our model case. And in particular, although I will consider the case of Rd, in general, I indicate by X the space where the source measure lives. And the source measure is indicated most of the time by mu. And Y is the space where is the target measure. That is mostly indicated by mu. So you think about the case x equal to y equal to Rd. And another important notation is P of x, that is the set of probability measures over x. So let me start now with several basic definitions. So the most important definition will be the one of transport map, but to define a transport map, let me first define a push forward. So definition, push forward measure. So let t from x to y, then mu is in P of x, mu is in P of x. We define the image measure or push forward, the measure t push forward mu in P of y, such that t push forward mu of A is mu of the pre-image of A for all A Borel sets in Y. Let me explain with a picture. In the case of transport map. So if now mu is in P of x and mu is in P of y, a map t from x to y is called a transport map if t push forward mu is equal to nu. So let me show with a picture this. So this is x, this is the space y, this is the measure mu, and this is the measure nu. So we take a Borel set in U, this is A. So T sends mu onto nu. So T is a transport map if we have that T is the push forward of mu on nu, and the condition is that mu gives to the Borel set T minus 1 of A the same weight, let's say the same mass that nu gives to the Borel set A. Okay? So the natural first question that we have to ask ourselves is whether these transport maps always exist or no. And unfortunately, one of the main problem we will see, one of the main problem in Monge formulation compared to the Kantorovich formulation is that optimal transport map and transport map in general don't always exist. So remark. So given mu and nu, the set of maps such that T push forward nu is equal to nu, so the set of transport map from nu to nu may be empty. Think, for example, to the case of mu equal delta in x0. So if mu is a Dirac delta centered in x0, then the T push forward mu is necessarily the Dirac delta in T of x0. So unless nu is a Dirac delta, then the set of transport map from nu to nu is empty. Okay. So let me now go on to another fundamental definition that is the one that will be used to define the Kantorovich problem of optimal transport, and is a definition of coupling or transport plan. So definition or transport plan. So the term coupling is mostly used in probability, but we can use both terms. So we call gamma a measure in the product space x times y, a coupling of mu and nu if mu is the first marginal of gamma and nu is the second marginal of gamma. That means that the push forward of gamma, with the first projection is mu, and pi y push forward gamma is nu. So pi x is the function that associates to the point x, y, x. So it's the projection of the first variable, and pi y is the projection of the second variable. So here, let me do another picture. So this is gamma, this is x, and this is y. And if we take the projection pi x of gamma, we will find mu. And if we take the projection, the projection pi y of gamma, we will find nu. And this is fundamental for what we will say in the following. So I recall that gamma is a measure on the product space. So we denote by gamma of mu and nu the set of all couplings. Of mu and nu. Okay. So now an important remark is that given mu and nu, the set gamma of mu nu is always non-empty. For example, the measure mu tensor nu is an admissible coupling. So it's a coupling of mu and nu. So belongs to gamma of mu nu. And this is another big difference with the notion of transport map, that a coupling between two measures always exists, while a transport map from two measures is not always necessary that it exists. So again, on this subject of transport map versus transport couplings, so it's important to note that if T from X to Y is a transport map from mu to nu, so satisfies that T push forward mu is equal to nu, then there is a natural way to induce a transport coupling between mu and nu using the map T. So we consider the map identity times T that goes from X to X times Y and associate to X the graph of T. Then gamma T defined as the push forward of mu, the push forward of identity times T of the measure mu is a probability measure on X times Y and belongs to gamma of mu nu, so it's a coupling. So any transport map induce a coupling gamma T. This is another fundamental notion. And this was covering essentially the basic definitions that we needed to now be able to explain Monge and Kantorovich formulations for optimal transport. So Monge. So assume now, again, mu in P of X, mu in P of Y. Assume C to be the cost that goes from X times Y. Assume the cost to be bounded from below and continuous. So now a little disclaimer. I will only mention theorems and formulation in the most, let's say, in the easiest possible setting, but several things can be relaxed and put in greater generality, but for simplicity, I will just talk about continuous cost here. So the Monge and Kantorovich problems can be stated as follows. So the total Monge transportation cost between mu and nu is the infimum on all transport maps of the integral on X of C of X T of X d mu of X. So the infimum is taken on all the transport maps from mu to nu. And I will call this M. So this is the Monge problem. While the Kantorovich problem, so the total Kantorovich transport cost between mu and nu is the infimum on all the transport plans of this quantity, that is integral on x times y, c of xy, d gamma of xy, such that gamma is a coupling between mu and nu. And you see also that the Kantorovich problem is much more symmetric than the Monge one. So there are a lot of indication that solving the Kantorovich problem is easier than solving Monge problem. In fact, for example, already Monge problem consists in minimizing the transportation cost among all transport maps, and this set of transport map we have seen that can be empty, while Kantorovich consists in minimizing on a set that is never empty. for example. So we call optimal transport map, so optimal transport map or coupling. The map or coupling that realizes CM or CK. So the map / coupling. Okay. So now we have a definition of optimal transport map and optimal transport coupling. Another remark is that we know that if T push forward mu is equal to nu, then the associated coupling gamma T can be taken considering the graph of T push forward mu. And in addition, T and gamma T have the same cost. Therefore, the total Monge cost between mu and nu is always larger or equal to the total Kantorovich cost. Okay. Now, some natural questions at this point consist in asking whether minimizers exist. So, do minimizers of M or K exist? And if yes, can we characterize them? So can we say something about their structure? And let me start from the existence of an optimal coupling, from what I've already mentioned. In general, solving the Kantorovich problem is easier than solving the Monge problem. So also for existence, a natural strategy is to first prove existence of an optimal coupling and then try to prove existence of an optimal transport map. So theorem. So let C a cost that is bounded from below and continuous. Mu in P of X, mu in P of Y. Then there exists an optimal coupling. Gamma bar in gamma of mu. And then once we have existence, the second natural question is about uniqueness. So is gamma bar unique? And if in general we have found this optimal coupling, we know that every transport map induces a coupling, but here we can ask ourselves, is gamma bar induced by transport map? So in general, just to have some intuition of this, about the possible answer to this question, let me give you a couple of examples. So just to, okay, so examples. Okay, assume that mu is a delta in x0. So we have x0 and we have a delta, so we have mass 1 here. And nu is 1/2 delta y0 plus 1/2 delta y1. So there are other 2 points, y0 and y1. And here we have mass 1/2 and mass 1/2. So there is only, let's say, the only thing that we can do is to send from x0 1/2 to y0 and 1/2 to y1. So it exists unique a minimizer that is gamma bar equal to 1/2 delta x0 y0 plus 1/2 delta of x0 y1. But of course, as we said, this is not induced by transport map. So we already answered to the second question, that is not, let's say, is not necessarily induced by a transport map. Second example, we assume x equal to y equal to R2. The cost is quadratic. And let's put 4 points. So x1 is in 0, 0. x2 is in 1, 1. Then we have, okay, this should be 1, 1. 1, 0. y1 is in 1, 0. And y2 is in 0, 1. So, and suppose that mu is now 1/2 delta x1 plus 1/2 delta x2, and mu is 1/2 delta in y1 plus 1/2 delta in y2. So how can we send mu onto nu? So we can start from x1 and we can say, okay, let's now send a quantity alpha in 0, 1/2 in y1, so include, and then we send the rest, so 1/2 minus alpha to y2. And let's do the same from x1. So here we send alpha, still in 0, 1/2, and then we send the remainder 1/2 minus alpha on y1. So we see that the couplings given by alpha delta x1 y1 plus 1/2 minus alpha delta x1 y2 plus 1/2 minus alpha delta x2 y1 plus alpha delta of x2 y2 with alpha in 0, 1/2. These are all optimal. So these are all optimal couplings. And this rules out the uniqueness without further assumption. And this was, in a sense, predictable because the Kantorovich problem is a linear optimization problem over a set with convex constraint or linear constraint. So a priori, since the problem is linear in gamma, there is no reason to expect uniqueness without any further, let's say, hypothesis. And this is what I wanted to say about optimal transport maps and optimal transport couplings, and about the existence of an optimal transport coupling. And let me now present very briefly the Kantorovich duality. That is a very powerful tool from both the theoretical and numerical point of view. So I will not directly use the Kantorovich duality today simply because I'm not entering in the proof. But you will probably see dual problems in the following lectures. I will give first the general theorem of Kantorovich duality, but also the version that was originally proposed by Kantorovich for the distance cost function, because that version is really simple and useful. So let me now go to Kantorovich duality. So as many of you know, if you have a linear minimization problem with convex constraint, in general, it admits a dual problem that is formulated as a maximization problem. And this is just because of now theorems in convex analysis. So in this specific case, we have C, the cost, continuous, bounded from below. And now assume that the inf on gamma coupling between mu and nu. So this is essentially the Kantorovich problem. I'm sorry, this is not the X, this is the gamma is finite. Then we can reformulate this problem in the following way. So we can, this is our primal problem. I'm sorry. Let me write it below, actually. So we have that the minimum on gamma in capital gamma or mu nu of the integral of C d gamma. This is our primal problem. This is equal to the max on phi of x plus C of y plus C of x y larger than 0. We'll put a plus here just to show that it's the same equation of integral of minus phi d mu plus integral of minus C d nu. And this is our dual problem. So we can transform a minimization problem or in a maximization problem. And you can see that now, for example, you have that mu and nu in the primal problem appear because they are in the minimization. So we are minimizing on the couplings between mu and nu. While here they appear in what I'm minimizing, so in the integrals, and at the same and in the same way, the cost in the primal problem is in the integral, while here the cost is now in the constraint. And this is very common in convex analysis. But let me now show the special case that was introduced by Kantorovich himself. So again, we have x equal to RD, and now the cost is x minus y, so the Euclidean distance. Then the minimum on gamma where coupling between mu and nu of integral on x times y of the Euclidean distance between x minus x and y in the gamma. This is equal to the max over phi of all phi 1 Lipschitz function of what? Of integral over x of phi integral over y of phi d nu minus integral over x of phi d nu. And by 1 Lipschitz, I mean simply that phi of x minus phi of y is smaller than x minus y for all xy in x. So it's just Lipschitz with constant 1. And this Kantorovich duality in the case of the cost x minus y is very simple, so it was really widely used. In particular, let me mention that this Kantorovich duality played a big role in proofs in kinetic theory, because one of the first proofs that used optimal transport in kinetic theory has been the proofs of mean field limit in the case of Vlasov equation and in general the well-posedness of Vlasov equation by Dobrushin, that in the 70s used the bounded Lipschitz distance, or the one Wasserstein distance, and in general this Kantorovich duality to show that if you have two solutions of this equation, of this Vlasov equation, then you have stability. And this was very useful since then. But by the way, Dobrushin was also the person who assigned the name of Wasserstein distances to the distances of optimal transport. And this was a bit unfair because actually Kantorovich introduced those distances, but Dobrushin at the time was not aware of his work. So Dobrushin is the culprit of why we really use Wasserstein distances instead of Kantorovich distances. And let me now go on. So we are now ready for the Brenier theorem. That is really a cornerstone of the optimal transport theory. I will state the Brenier theorem only for quadratic cost, even if it applies also more generally to several strictly convex costs. But let me state it in the simplest possible way. So let x be equal to y, be RD, the cost be quadratic. Suppose that the integral over RD of x squared d mu plus integral over RD of y squared d mu is not infinite. So yeah. Then assume that mu is absolutely continuous with respect to the Lebesgue measure. Then we can say that there exists a unique optimal transport coupling between mu and nu, gamma bar. And moreover, what we can say is that gamma bar is actually induced by a map. So is induced by map T. T now is an optimal transport map, but on top of that, we have a structure that is that T is the gradient of phi for phi convex. So not only we have an optimal transport coupling, but we have that the coupling is induced by the map, and that the map has actually a lot of structure because it's the gradient of a convex function. And you know that convexity in optimization problem is really a key let's say, feature. And in particular, the fact that the optimal transport maps are gradient of something. So the role of the gradients of functions is really central in the optimal transport theory, and we will see it also when I will formally introduce autocalculus. So there is, as I said, there is an analog for the cost x minus y to the p with p strictly larger than 1. In this case, we have to require that we have bounded p moments. So instead of the power 2, we shall have then here the power p and here. And in that case, we have existence and uniqueness of an optimal coupling gamma bar, and is still induced, this gamma bar, by some transport t, but in this case, t is not the gradient of a convex function, but is more complicated. It comes with a more complicated formula that is less useful in general than the one that we have in the quadratic cost. So let me give you now another definition. So we want to arrive to the definition of Wasserstein distance. So first, we need to define the space of probability measures with the finite p moment. So, oops. Probability measures with finite p moment. So again, let x equal RT. Let P be in 1 plus infinity. Then we call capital P of x the set of all probability measures on x, sigma, such that the integral over x of x to the power p in the sigma of x is finite. So this is also referred to as moment condition. So this is okay. And now that we have the space that will be the protagonist of the following, I can finally define the Wasserstein distances. So definition, P Wasserstein distance. Probably I will change page, I'm sorry. So given now two measures mu and nu in the space of probability measures on x with finite p moment, then the P Wasserstein distance between mu and nu is defined. We take the infimum on all the couplings between mu and nu of what? Of the integral on x time y. Oops, in this case is x of x minus y to the power p d gamma of x and y to the power 1 over p. So we see that this is the power 1 over p of the optimal transport cost by Kantorovich. So we have that the relation of these distances with the optimal transport problem is very crystal clear, because it's really defined in this way. And it's not very easy to prove, in particular the triangular inequality, but we can prove that the P Wasserstein distance, so the W, so Wasserstein P is a distance on the space of probability measures on X with finite P moment. So we will refer to PP of X with the distance Wasserstein P as Wasserstein space. And these Wasserstein distances are really exceptionally useful and in many sense easy to work with, in particular in the case of the two Wasserstein distance and of the one Wasserstein distance that I use it for different situations. In particular, a very nice feature of the Wasserstein distances is that they're very weak norm, but we have this theorem that tell us that suppose that we are in a compact set, for simplicity, we set everything in compact sets. Then, so P larger than 1, if we have mu n, a sequence of probability measures on X, and mu a probability measure on X, then we have that the Wasserstein distance, the p-Wasserstein distance, is equivalent to the weak star convergence. So saying that mu n weakly star converge to mu, in this case, is equivalent to say that the p-Wasserstein distance between mu and nu tends to 0. So on compact sets, the Wasserstein distance convergence is equivalent to the weak star convergence, and this is also a reason why these distances are very practical with respect to other distances between probability measures. Think also about the simple fact that, for example, if you have two Dirac deltas centered at two points, x0 and x1, if you consider, for example, the total variation distance between these two deltas, the total variation distance is always equal to 2, no matter how close are the supports of these deltas. While the Wasserstein distance instead between two delta of Dirac is essentially the Euclidean distance between the support of the deltas. You can do this as an exercise. So it's a distance that is very sensitive also to atomic measures, and this is great for many applications. For example, this is great in kinetic theory when one wants to derive equations from particle models. So, but come back to optimal transport. We now are left for this first hour with the construction of geodesics. So X now is again equal to RT. Assume that mu0 and mu1 are probability measure on X. So we have mu0, we have mu1, and we want to construct, so we have a transport map T, and we want to construct a geodesic. So we want to, in a way, interpolate mu0 and mu1 using this optimal transport map T. Okay, so if T is the optimal transport map between mu and nu, I'm sorry, mu0, mu1, in this case it's easier. mu1, then the geodesic mu t takes the form of t, so a map t push forward mu0, where this map tt is the linear interpolation between the identity map and t. So tt of x is defined as 1 over t minus t x minus t of x. So so by geodesic, we can always have in mind, if we want to think about the geodesic between 2 points, is the shortest path between these 2 points informally. And with this definition of geodesic, we can say that in this case, that T is an optimal transport map, the geodesic mu T is also said to be a constant speed geodesic. So the geodesic mu T is constant speed. That means that if you take the p-Wasserstein distance between mu s and mu t, this is t minus s, the Wasserstein distance between mu0 and mu1 for all s and t between 0 and 1. And okay, I've not mentioned here, but mu t are all measures in the space P of x, so the space of probability measure with finite P moment. And let me briefly mention that in the case that we don't have at our disposal, so it doesn't exist an optimal transport map, there is also a formula that is equivalent, but in the case of having an optimal coupling. So a formula that is expressed in terms of the coupling. And I don't really know with the delay at the beginning how much time I have, but I can stop here for this first hour, and then we can start again with the introduction to gradient flows.
Okay, thanks, Mikaela. Are there any questions? Is there any question for Mikaela? Maybe I have one just on the Grenier theorem, like when you have a cost which is a strictly convex function of x minus y. So you said that we have the existence of the optimal transport map, but that is not necessarily the gradient of the convex function, right? So,
yes.
So when is this true? It's only for the two.
So in this case, so if the cost between x and y is, for example, x minus y to the power p, with p strictly larger than 1, then we don't have that t is the gradient of a convex function, but we have something like t is equal to grad phi modulus of grad phi p minus 2 with phi p convex, something like that.
All right.
I'm not really sure of the formula, but there is a formula that relates the optimal transport map with gradient of functions.
Okay, thank you.
Again, so you're welcome.
Good question. So thank you. We'll be back at 11:15 because we're a bit late on the schedule. Sorry for that. But thanks, Mikaela, again.
No, thanks to you. See you soon. Bye.